For the practical part of ADL4CV, we've been working on multi-scale style transfer, and today we would like to present our project. Style transfer can be thought of as synthesizing information between two domains. In our task, given a content and a style image, we'd like to generate a new output by keeping the geometry and the structure from the content image while resembling the style. SingN is the main work that inspired us for this project. They use a multi-scale architecture to learn image generation from a single training image. They are capable of learning patch statistics of a given image so that they can generate unique variants of that image at each forward pass. Another interesting work in the literature is adaptive instance normalization. ADL layers are capable of transferring information between two streams by aligning mean and variance of their feature maps. Inspired from both of these works, our main goal and contribution is to perform single image pair style transfer in a multi-scale fashion. With our multi-scale architecture, we are aiming to capture finer details, and we want to explore the generalizability of single image pair learning for style transfer task. For this task, we have two promising approaches that builds on top of each other. First one uses a pre-trained VGG network to calculate losses. Second one takes it one step further and combines it with an adversarial training scheme. Here in the figure, you can see our first architecture for a single scale. We have two heads encoding information coming from a style image and the upsampled previous scale output. With the help of ADN layers, we obtain a stylized content image at the output. Then we feed this output into a pre-trained VGG network to calculate style and content losses, which are the main objectives of our training. Of course, the output of this scale is fed into the next scale, and training procedure continues recursively.
A second promising approach retains the discriminator in addition to VGG. We perform two forward passes using our network, both with different inputs to ADN. In one case, we input content into ADN, in which case the resulting stylized image should be exactly the content image. This stylized image, together with the original content image, compute the content loss using a discriminator and an L1 loss. In the second case, we give ADN the style input as input. Here, the stylized image would be the desired result of style transfer. This resulting image is then compared to the style image using VGG to compute a style loss. Here, you see several results of both our VGG approach and the discriminator approach. We then compared our results to several baselines. The first baseline is CycleGAN, a method trained on large datasets of images. TUIGAN is the most recent method and solves the most similar problem to ours. It performs unpaired image-to-image translation using two multiscale architectures. One network learns content to style mapping, while the other learns style to content. ADASYN originally was supposed to be a single scale of our model. However, a single scale turned out to be incapable of producing comparable results, and therefore we extended the single scale to a UNet-like architecture that also incorporates ADN. Lastly, you see our VGG and discriminator approaches. We evaluated our results in a user study, where we conducted a two-part survey that we used to compute the deception rate and the user preference. We had 38 responses in our survey for the first part and 32 responses for the second. The deception rate measures how often the participant confuses one of our generated images for a real image. In the second part of the survey, participants are asked to rank the output of different models based on how well they believe this model performed the task of style transfer. The top one score measures how often the model outputs were marked as best result, while the top 3 score indicates how often the model output made it into either first, second, or third place. Outputs looked exceptionally well for certain models in particular cases, which caused a high top 1 score. However, these models may not perform as well in the general case. We hope that the top 3 score more clearly indicates how well the model performs in a general setting. Thank you for listening. We hope that our project was interesting, and we eagerly await your questions in the Q&A session.